Well, it's a great delight to welcome back Chris Isham for the session this afternoon, and we're going to give him another introduction, especially for the camera as well. He's, as you know here, Professor of Theoretical Physics at Imperial College in London. He's also the Dean of Natural Sciences there, and he's very widely known for his work on quantum gravity and indeed in the whole area as well of this discussion between science and religion. I've just been hearing from Chris some of his other interests and backgrounds, and he actually sings Gregorian plainsong in his spare time, which has somehow fitted into all the other things. He's also started off life as an engineer and built a huge flight simulator as well, as just another kind of hobby going on in the background. So someone with a huge range of gifts and interests. And it was Paul Davies, apparently, who said that Professor Isham was the greatest expert on quantum gravity in Britain. So I've been allowed to say that and to re-quote it. And it can be interpreted, apparently, a number of different ways. But so we'll leave it at that. But I got special permission to say that as part of the introduction. I hope. I'm sorry we don't have his book, the edited book, Quantum Cosmology and the Laws of Nature. We don't actually have it on the bookstall. But I will just wave it around, as I think Rodney did this morning as well, as a book that Chris has been very much involved in. So we're delighted that he's going to speak to us this afternoon on the subject of quantum theory and being.
Thank you very much. Well, you heard me this morning, of course, but that was just me warming up my vocal cords, really. This afternoon is my serious talk in this meeting. So, what am I going to talk about? Well, let me start off. I'll give you a wonderful quote from Heidegger. Heidegger, of course, wrote many things, most of which were fairly incomprehensible. There's one particular book he wrote called What is a Thing?, which is not very well known. I think it's a marvellous book, and it's one of my favourite philosophy books, actually. And there's this quote right at the beginning. This is how the book starts. It says, "From the range of basic questions of metaphysics, we should here ask this one question: what is a thing?" It says, "The question is quite old. What remains ever new about it is merely that it must be asked again and again." I think actually it's a fantastic quote which all philosophy students should have over their desk. Now, of course, you couldn't actually have it as a philosophy student, because if you're doing modern philosophy, you're allowed to ask questions like this, of course. It's not consistent with what you're supposed to do these days, but nonetheless, it's a wonderful question. And because it gets to the very heart, plus all the things that John was talking about this morning, the whole question of critical realism, whatever, is about what are things. If you're a realist, the world is about things as you encounter them in space and time. So things is one part of the trinity of thing, space and time. Now, what is interesting, about 50 pages into the book, is Heidegger answers his own question. Here's the answer he gives. A thing is always something that has such and such properties. Always something that is constituted in such and such a way. And here's the key sentence. This something is the bearer of the properties. The something, as it were, that underlies the qualities. Now, what he's saying there is a thing is something which has properties. So it's determined by properties. It has a bundle of properties. And that's exactly the picture of classical physics. That's exactly the philosophical state of view of classical physics. Now, Heidegger famously knew almost no science at all. He was not a scientist, really like that. Nonetheless, and he certainly wasn't afraid, I'm sure, with the philosophy of classical physics. But what he's said here is exactly classical physics. Now, also, of course, is common sense. I mean, it's the common sense view of reality. It's a view which, well, I've called it simple realism. People sometimes call it naive realism. It always sounds vaguely impolite to those people who actually adhere to it. So I call it simple realism. And it has interesting relation to knowledge, epistemology, because it's what John was saying exactly this morning. Is that in this view, if you measure something, what you measure, what is actually there. So if I want to measure the position of something from here, say, and I get 20, 30 centimetres, if you say, well, why did you get 30 centimetres? The answer is, well, that's because the particle was. What I measured, it simply reflected what was actually the case. And then a good measurement is simply something which reflects most accurately what is actually the case. So this is fundamental in classical physics, and it reveals the way things are. And as John says, I've talked with John lots of times over the years, he has on his T-shirt, most famously, this slogan embroidered epistemology models on tautology, precisely saying this. So unknown to John, I'm sure he's unknown to John, he's a Heideggerian fan. I'm sure you wouldn't agree with that if he was here. But anyway. Now, as he explained, he and his colleagues developed this simple realism, something they call critical realism. Now, actually, I was a bit misled about this. I think Arthur Peacock and John Polkinghorne and Ian Barber were the three people who most developed this philosophical view. I mean, they're the ones most well known for it. Well, I'm quite sure that one of them told me the reason it was called critical was because it was based on the critical philosophy, which means Kant's philosophy, and it took into account Kant's ideas and developments from there. Now, from what John was saying this morning, he wanted to distance himself from the ideas of Kant, so he was using the word critical in a more ordinary sense of the use, just like being careful. But I'm taking the Kantian view seriously, and in fact, very often, Philip Johnson here, I always enjoy putting his leg about this, you see. He says he's a critical idealist, a critical realist. I would say my philosophical position is mystical idealism, see, which is the exact opposite of critical realism. Now, personally, that's actually true. I'm a mystical idealist, through and through. However, I have to say, it doesn't get you very far doing science being a mystical idealist. So, first of this talk, I'm taking critical realism very seriously, particularly the ideas of Kant very seriously. And I'll try and explain what I mean by all this. Now, I mean, one thing you might perhaps, or might even wonder, may have asked yourself, when you looked at the structure of this meeting, was it's called God and Physics. Almost everybody's talking about, not everybody, almost everybody's talking about quantum physics. And of course this happens every time. Whenever I get roped into these meetings, I'm always asked to talk about quantum physics. If I wasn't, I would anyway. It's true. People ask me to do. So quantum physics somehow is thought to be particularly appropriate. Now, I think we need to be very careful here. I'm actually as it happens, also a keen fan of Whitehead. And he had this wonderful thing which he called the fallacy of misplaced concreteness. And this was what he felt was the tendency of people who reify things when they were talking philosophically, particularly about science or religion, to make real something which really was an idea. So he warns against this. Now, that was Whitehead. Now, Chris Isham has something which is called the fallacy of the equality of mysteriousness. It works like this. Here's the argument which people sometimes use. They say quantum theory is mysterious, and God is mysterious, therefore there must be a link between them. Now, that's of course not true. But many people, actually, if you look at some of the, these days, of course, on the internet, if you type God and quantum theory, you get about 1 million hits or something. There's always discussion groups going on. But if you look at them, you'll find an awful lot of them actually are simply doing this. They are simply saying, well, quantum theory, oh man, because they usually come from California, spaced out. And God is presumably spaced out too, and so they're put together. Now then, here's another caution run. The job of theoretical physicists, do theoretical physics, not philosophy. This is something, again, I think my colleagues should remember. And I'm actually extremely interested in philosophy, but nonetheless, I'm not a professional philosopher. So I try to be cautious about this. So why do I talk about Kant, apart from that I like Kant? Well, as John explained this morning, I mean, what Kant's ideas was somehow that when a human being, particularly a human being, studied the world, as it were, whether you may mean by that he or she would bring to bear automatically, of necessity, a priori, as he called it, certain categories of thought. And Kant felt these to be inevitable. And he said, you can see, therefore, of necessity, we will model the world according to these different categories. Now, when I first read this, I was quite overwhelmed at how what a profound idea that actually was. And certainly, it's had a major impact on philosophy since that time. Now, as John said, it's also true that some of Kant's categories look a bit shaky these days. But there's another form of Kantianism, which is very rarely commented on, which is what I want to talk about, which is the same thing but applied to mathematics as is used in physics. So in other words, if we apply mathematics to physics, which of course is what we do all the time as theoretical physicists, particularly as quantum physicists and theorists, then we are bringing to bear mathematical ideas to describe the physical world. Now, I would claim, and I want to explain what I mean by this, that actually hidden in mathematics there is in fact a profound interplay between the mathematics we use in theoretical physics and the often implicit metaphysical framework. In other words, what I mean by this is a certain mathematical structure, something which seems so obvious that we use it without thinking, automatically, I mean, you really could use the word a priori, actually, in the way Kant said, enforces a priori a certain view of the world. And therefore, if you use the wrong mathematics in the wrong place, you commit a category error, and that's what I think we do when we're talking about quantum theory, actually, as I want to explain. Okay, so, in particular, a question I want to ask is this. Now, I really put this in for John. John was very apologetic he couldn't be here this afternoon, he's not making it wiped out, but I put this in for his benefit, really. Is there a mathematical underpinning for critical realism as Boolean algebra underpins simple realism? What do I mean by that? Well, when people talk about simple realism, part of what they mean, inevitably, whether they're philosophers or theologians or physicists or just the man and woman in the street, is the use of Boolean logic, Boolean argument. So you have the notion of propositions about the way things are, you use the connectors like and, or, not. And you manipulate in a way you all know very, very well. And that's what we do, right? And we do it almost automatically, really. Now, what I want to talk about today is whether or not there's a mathematical structure that goes beyond that. I'll explain what I mean, but Boolean knowledge is a very, very special thing, it turns out, in mathematics, and is the way of getting beyond Boolean knowledge. You have to just bear with me for this, we see what I'm going to talk about. Now, I've got a warning here, this is not an easy lecture. Because when we teach people to teach it in Pure College, we didn't in my young days, of course, we simply did it. First thing you tell someone, if you're teaching, don't say this is going to be hard, because it puts the audience off. Actually, my experience of undergraduates, that's not true. If you tell them this is going to be really hard, they go, oh, they get really excited. It's like if you've got a PhD student, or sorry, a prospective PhD student, and says, I want to work on something, you say, oh, this is very, very difficult. You've hooked them. So I'm hoping I shall hook you with the content. It's not an easy lecture. Well, maybe for physicists, it won't be for the theologians. Now, let me make something clear before I do this, is that what I'm going to say is not speculative. I'm not talking about Chris Isham's wild and wacky theory of theoretical physics, which he's gotten because he's over 45 years old, as not so politely remarked. That's not true. I don't have any wild and wacky theories. What I was going to talk about is some very fundamental ideas in mathematics which affect directly the way we use maths in physics. So if you like, this lecture is aimed at the link between philosophy and mathematics, and physics in a very general sense. And in fact, though I called the lecture Quantum Theory Bring, there's actually no quantum theory in it, or hardly any. It's just the motivation, which is just as well, because the next lecture I see from his transparencies anyway, we'll talk a lot about quantum theory itself. But let me start off, and you'll see what I mean as I perhaps unpack what I mean by saying there's a philosophical position locked into mathematics. Let's take ordinary classical physics for a moment. Let's consider reality. Use the word reality seriously, or realism, if you want. I wrote a book on quantum theory, and I'm very careful when I wrote this book because I really wanted to get the philosophy right, you see. And in various points, I talked about realist philosophies. You see, the desk editor very kindly changed it to realistic every time. I couldn't believe it. I had an argument with the publisher about this, and this, I mean, it wasn't even English. I won't say it was. It wasn't part of the English. It was, so this non-English person was arguing with me about the English language. Anyway, I got it through, but it has some. Okay. So this is reality in the sense of realism, not realistic. Now, let me go back to Heidegger. See, what he actually said was that essentially a thing is defined by its properties. Now, if you're talking about physics and physical system, which I am, this means the values of all physical quantities. So of any physical system, we have an idea of what is physically interesting pertaining to that system: position, momentum, angular momentum, charge, whatever, it doesn't really matter. So if you know what these things are, they're of interest to you. And what you're saying is that the thing in its entirety is really determined by, or determines, two are almost synonymous, the values of these physical quantities. Or if you like, it will give you a straight yes-no answer to any question. Is the value of the energy 6.6? The answer is either yes or no, because the actual value of the energy adheres to the system. So this is the Heideggerian view, if you like, and it's exactly the way, say, classical physics works. And this is encoded in the notion of a state. When I was a student, I remember I was an undergraduate doing a physics degree, I was always very mystified by the word state. I mean, lecturers tossed it around all over the place, and I never knew what they were talking about. And when I actually asked them, I didn't get a very satisfactory reply. You often don't if you ask questions like that, actually, because people get so used to the terminology of that subject, they're not really thought about what it actually means. In any event, what you could say a state really is that a state is something which specifies precisely the values of all physical quantities. In other words, what we mean by a state is a mathematical entity which, if you know what it is, automatically gives you the values of all physical quantities. It's a very good definition of a state, actually. And it's extremely important because that simple state, which you may think is obvious, already automatically imposes a logical framework on physics. Just that simple requirement that you have a notion of a state which tells you how things are, automatically, a priori, imposes something on the way you view the foundations of physics. Now, I want to illustrate that with a couple of diagrams. If you're not a mathematician, I apologise for somewhat obscure looking nature of these diagrams. They're really meant to be guides to the eye, really. So what I'm saying here is that the way you work with classical physics, which has this sort of philosophy, is you start off with some sort of space, I call it sigma, some collection, it's a set of something called states. So it's actually points, doesn't mean what they are, just mathematical points. If you know what the point is, you know what the values of all physical quantities are. So let's take a physical quantity A, then since the values of all physical quantities are supposed to be numbers, real numbers, that means irrational numbers or whatever, what you can say is, well, a physical quantity is always represented by what mathematicians called a function from this space to that space. In other words, to each state S, you associate a real number, and that is the value of that physical quantity. Now, this is very, very elementary mathematics, actually, but it's extremely profound and automatic what it tells you about how you're going to describe the physical world. Now, I want to emphasize this picture of necessity follows from Heidegger, basically. It's not how you normally present it, but it's true. Of necessity, if you regard things this way, you will have this picture. There will be something called the space of states, the way things are, if you like, and for each one of these, for each physical quantity, there will be some association for each point in the space to a real number. Now, mathematically, you write this like, this is just the way mathematicians write these things, and it just looks nice, I write it up. We'll come back to the why, write it quite the way a bit later on. But that's what you have. Now, why do I emphasize that? Why is that so important? And the answer why it's so important is that immediately you get a take on logic. Now this is called a classical breakfast. I don't know, did any of you see New Scientist article by any chance? You didn't, just as well, all right, okay. Good. No one reads the New Scientist. they did something about this, they made a complete talks read of it. Okay. Now here's the point. That a simple idea as what people will call Venn diagrams automatically implies that propositions in this type of physics satisfy a Boolean logic. In other words, the nature of the logic of the way we talk about the world is not optional. It's automatically determined by the mathematics in advance, because the mathematics itself has this built into its foundations. It's a very, very simple idea, this. Let me state what I mean. Suppose we have some physical proposition P, which is say the energy has a certain value. Now, for each given state, it'll either be the case it's true or false, because either it doesn't, it doesn't. So you can collect together all those states for which it's true and think of them as this sort of shaded area. So each proposition is associated with a certain subset, say, of states. Those states which each proposition is true. It's a very simple idea. And in proposition Q, the same thing applies. Another proposition Q is you have this subspace. Incidentally, this would work for anything, not just physics, of course. Anything where you talk about states of affairs, you know how things are, you could model in this way. Now, suppose I ask what we represent with the proposition P and Q, the logical connectives. Well, what does that mean? Well, P and Q presumably is true. For all those states which P is true and Q is true, which is just this intersection here. And similarly for OR, you can argue that it's the union of the whole two and simplification. Now, why is that significant? The reason why that's significant is if you then look and see how these unions intersections behave, they automatically satisfy a Boolean logic. It's one of the basic theorems of mathematics, in a sense, it's very elementary, is that the subsets of the set give you a Boolean algebra. As a matter of fact, every Boolean algebra is of that sort, basically. Now, what this means is the following. The eggs and sausage and bacon paragraph. If you're in a hotel, or indeed, this morning at breakfast, when you were served breakfast, if the young lady serving breakfast said, would you like eggs and sausage or bacon? We assume that Templeton Foundation Committee ran out of cash a little bit, so they're strictly what we can eat. Eggs and sausage or bacon, you would construe as meaning you've been offered eggs and sausage or eggs and bacon. I think most people would. And that's the so-called distributivity property of ordinary classical logic. And that's automatically true. You can easily check, it's a simple Venn diagram stuff, but even kids do at school these days. You can easily check it's automatically true. So what this means is any propositions you make about the world of necessity will satisfy this type of logic. Actually, to celebrate this point, this morning I did in fact have deliberately eggs and sausage from bacon. It's the first time I had a cooked breakfast about 10 years, I think. It was a sort of symbolic thing for me to do. Anyway, so that's the thing. Now, this doesn't work in quantum theory, most famously. But it looks automatic. And it is automatic in classical physics. So you don't have any option about this. Right? People don't always realise this, that the way you talk about the world using classical physics is that you can't do anything about it. It's automatic because it's a priori in the mathematics, in the way Kant would, I think, have appreciated, actually. Okay, so that's the point I want to make at classical. Now, when we come to quantum physics, this is utterly different. Now, I'm not actually going to say very much about quantum physics. Matter of fact, there's not very much more than this one box. But as you've heard, and of course most of you know already anyway, quantum theory is most normally presented in a purely instrumentalist way. When I'm lecturing to students, I always call this the dollar interpretation. It's the interpretation that Intel used to make vast sums of money when they make their semiconductor devices, because it simply works. I mean, there's no question about this. The instrumentalist interpretation of quantum theory simply says what would happen if you make a measurement is spectacularly successful. There's no known violation of it anywhere. It's incredibly successful theory, spectacularly successful. And it works extremely well. However, for many physicists, even in the early days of quantum mechanics, of course Einstein most famously, many people say they don't like this. They feel this is not quite correct. Surely any decent theory of physics should in some way tell us how things are. I get back to Heidegger's view. Heidegger would have been quite shocked to be told this is what a theory of physics was. He wasn't interested in making measurements. He wanted to know what's actually the case. There's one wonderful phrase in another one of Heidegger's books. I couldn't find it, unfortunately. I'm going to put it on the transparencies, where he warns against this. Whatever happens, you must not confuse the beingness of being with the being of beingness. I ask you to keep that in mind as you listen to the rest of this lecture. This is a very deep thought. Right? The beingness of being, the being of beingness. Okay? So Heidegger took these things very seriously. In fact, written in Greek, they look even better. He always did write in Greek. So you may ask, well, okay, can you get out of this? I mean, many people have asked this question. Is it really the case that the reason why we get these probabilities is just like it would be in classical physics when you have probabilities? It's just a reflection of your ignorance about how the way things really are. In other words, is there actually a fact of the matter about how things are? Just you don't know what it is. This is where these so-called hidden variables come in and so on. And in fact, there's a very powerful mathematical theorem, which is a purely mathematical theorem called Popper's Becker theorem, which says you can't do this. It's a wonderful theorem, actually. It means in a sense the world doesn't exist. I always find this heartening when I teach students this. They always cheer up enormously when we sort of mathematics proves the world doesn't exist. But it doesn't exist in the classical sense. So the mathematical framework of quantum mechanics is such that, of necessity, again, you cannot impose a classical realism on it. Wherever hard you try, you can somewhere something's going to squeak. I mean, it's just true. And therefore, there are no consistent true-false assignments in quantum theory. That's absolutely correct. I mean, you can try and make the assignments non-consistent. I mean, anybody can say this proposition is true, that proposition is false, of course. You make no connection between them. You want some sort of logical consistency. This mathematical theorem, which is not that easy to prove, but it's certainly true, says you can't do it. So that's deep in the heart of mathematics. Now, what this means in practical terms is so-called quantum logic is non-distributive. I mean, there is a thing called quantum logic. I mean, you can look at the things that represent propositions in quantum theory, just as we have these subsets of the base of states in classical physics. You can see, what do they look like? How do they behave? Well, the answer there is non-distributive logic. And this is where the eggs and sausage and bacon particularly come into play, because there's a well-known situation in quantum theory where the following arises. If I go into the hotel, and the waitress or waiter says to me, would you like eggs and sausage and bacon? If I say eggs and sausages, they don't get anything at all. If I say eggs and bacon, please, they're going to get anything at all. The only answer you can actually give to the question is, would you like eggs and sausage or bacon, is yes, please. Because what you get is eggs and a quantum superposition of sausage and bacon. It's a very simple example. It's one of the simplest things to illustrate in quantum mechanics, actually, because even the most elementary amount of quantum mathematics. And it's quite striking. So it shows very dramatically. Now, I often say to students, well, after the lecture, go away and try and talk to each other without assuming distributivity. You can't do it. I mean, it's automatic. Our brains work in this way. In fact, many people have written quite seriously about this. They say we have Boolean brains. But the way our brains work, of necessity, is Boolean. Now, again, that's something Kant would have recognised, of course. There's a certain type of a priori superposition. Now, you may say, well, okay, where do you go from there? Well, an obvious problem is in quantum cosmology. Now, Don Page talked about this tomorrow morning, and I'm not saying about it, other than it's a big problem. If you believe quantum theory can be applied to the whole universe, maybe it can't. It's quite possibly it can't. But if you believe it can, then this is a big problem, because you cannot use an instrumentalist interpretation of the whole universe, because who's the measurer? I mean, it doesn't make any sense. You have to have some sort of realist interpretation. But it can't be naive realism, because that doesn't work. The theorem says you cannot use naive realism. So you really get caught, and people who work in quantum cosmology for many, many decades now have taken this very, very seriously indeed. And it's spawned off all sorts of strange ideas. I mean, some strange, some very strange, and some Don will talk about tomorrow morning, which are very, very strange. So there's a whole range of spectrum here, which people, but it's not a solved problem. Okay, so the obvious question is this. Can we regain some type of realism? In spite of its mathematical theorem says you can't, can you regain something? No, in fact, going back to what John was saying this morning, there are two demands for this. There's a demand from physics, which is the one I just said, about quantum cosmology. There's also perhaps a general feeling that Einstein had, that the theory that only could tell you what would happen if you made measurements was somehow not quite what you wanted as a scientist. That's the demand from physics. Also, there's a demand from theology. Well, there's certainly a demand from people like John, who want to talk about science and religion using the same philosophical framework. I mean, John, when he talks about religion, wants his statements to be true in the same sense the word true can be applied to statements about the physical world. And that's very important for John. It's an integral part of his whole way of talking about science and religion. And to him, critical realism means this. So the question is, can we kill two birds with one stone? In other words...
So what's S and R?
Sorry?
S and R is theology.
Science and religion.
Oh, yeah.
It's just... So, can we kill two birds with one stone? Is it possible to find some sort of mathematical framework, whatever it may be, which is, if you like, satisfies the physicists, but also could be an underpinning of critical realism? Now, when I first started writing this talk, which was several months ago, I wasn't thinking of John Hockington. But I was thinking of something that work I've been doing with various collaborators for a number of years, or 10 years anyway. But as I started to write the talk, I thought, actually, I could be talking about John here. I mean, really, his demands are the same. I mean, it's the same, the psychological demand, whatever it may be, is something you may call realism. It's the same whether you're a theologian or a scientist. I mean, it's not really that much difference at the end of the day. You want to believe somehow you can talk about things being true. And this is not just a, a sort of a narrative you're telling. It's somehow real, if you know what I mean. Now, how can we do this? Because I've argued, first of all, I've said that quantum theory certainly doesn't do this. And I've also said that classical physics does. But the reason it does is because the mathematical framework of classical physics automatically produces it. See? Now, at this point, an interesting sort of possibility arises, which has intrigued me for some time, actually. Is there perhaps some relation between the foundations of mathematics and the foundations of physics? In other words, is it possible that the reason why quantum theory looks so strange, maybe why we struggle, not just in quantum theory, but all over the place, to use realist language where somehow you can't, so simply using the wrong sort of mathematics? Is that possible? And the answer is yes. But this is not just the wrong mathematics in the sense of the wrong branch of mathematics. What I'm actually talking about is the wrong foundations for mathematics itself. Now, when you first encounter this, if you know any mathematics at all, this comes to a huge shock. I mean, if you're a student, for example, doing physics or mathematics, it's not bad enough trying to learn mathematics you're taught. But when you do, when you've learned it, at least you think, that's it, I know it now. But then to be told, actually, there's zillions and zillions of different foundations in mathematics, all you've done is one of them. And you think, wow, my goodness, what's going on? And reasonably so too. But in fact, it's true. There are actually millions and well, not millions, a vast number of different foundations of mathematics. Maybe one of them is useful, talking about quantum theory. Maybe one of them is useful, talking about science and religion. I mean this perfectly seriously. I mean, whenever I talk about something, I always like tongue in cheek when I interact with John Tolkien or various historical reasons. But I mean this perfectly seriously, actually, because anything we call paradoxical, people call quantum mechanics paradoxical, and people, particularly non-believers, call theological statements or religious statements paradoxical. What they mean is it doesn't make sense within the normal sort of discourse that we use, which means ordinary, plain, honest, simple, naive logic for most people. So maybe it's not just a silly thing to do after all. It may sound rather extreme and pretentious, but like I said, this is not actually speculative. I mean, what I'm going to say is not speculative. The only speculation is it might be useful. That's the only speculation I'm about to tell you. I'm not going to invent some science fiction theory throw it at you. However, I'm afraid, of necessity, I have to do a little bit of mathematics, because after all, I'm talking about some deep relation between the foundations of maths and how we talk about reality. So obviously I've discussed mathematics. And when I wrote this talk, I realised there might be at least one person in the audience who wasn't a mathematician or physicist. So I've tried to explain in very simple terms. If I fail, I apologise. I cut it right down to the very middle. I always do this in my talks. I write them in a place. And I try and cut out transparency. I cut out sentences. I cut out paragraphs. So you get the absolute bare minimum, because my experience of lecturing, that's the most successful thing to do, actually. So I hope I've succeeded. If not, Professor, I apologise. So what I'm going to talk about, the ideas I'm talking about, go back to things I started with a philosopher here in Cambridge, German Butterfield, and more recently, well, various people in Imperial College, but other people do this too now. So let me try to explain. Now, the maths I'm going to talk about is certainly not my invention, but it's a new way of thinking about maths, which I'll explain when I get to it. It's shocking when I came across it. I sort of vaguely said this, and ordinary mathematics is based on the theory of sets. And what is a set? The set is a collection of things, broadly speaking. Actually, remember, I have two daughters, and the youngest one, the eldest one, sorry, was first going to school at the age of 5. My then wife and I trotted along, as you do, to the school to be interviewed, basically. It's that sort of school. You pay interview you, not the other way around. Now, our suitability, anyway, yeah, and we met the teacher, because they found this 5-year-old, you're one teacher for the whole, the subject, So I said to her, well, what do you do? She said, she said, we teach them the theory, we teach them about groups. I thought, oh. I told her my ex-wife was also a mathematician. We looked at each other and we thought, oh. 5-year-olds. I mean, you have to do a set theory before you do a theory of groups, was it? What she actually meant, they talk about playing in groups, you see. She actually meant. So you have to be careful. So set theory is the basis of mathematics. It basically sets a collections of things. And again, this seems so obvious. Someone's not a mathematician. You think, how can you possibly make a song and dance about this? But actually, there are many deep problems, or at least, seriously, paradoxes, or interesting questions in the foundations of maths. So a set is a collection of things, but set theory is not just about collections of things, it's about relations between sets. And I'll try to give this one fundamentally simple example. Suppose I have here 3 sets, collections of things. This is a collection of 5 people, called somewhat ingeniously P1 to P5, as physicists do. Here we have 4 possible nationalities, Indian, English, French and American. The first 2 play cricket, the second 2 don't, that's the main distinction between them. Then we have European and other. Actually, I should have put here cricket playing and non-cricket playing. I realised afterwards. Anyway, European and other. Now, of course, we can say of any person whether they're European or not. But we can also follow. We can first of all ask what is the nationality of the person. Now, we can think about it as a function from this set to this set, because to each point here, of all the functions associated with each one of these elements over there. So this first person, say, is Indian. So we put the arrow over across there. The second person says English, so we draw this out. The third person says Indian. The fourth is French, the fifth is American. So this is a simple example of a function that all it actually is. And of course you realise I used the same thing talking about physical quantities. Only here it was the space of states, and there it was the numbers. But it's the same principle. And now we can do this. We can now say, well, an Indian person is not European, so we associate with Indian the other. The English, of course, is European, so is the French American isn't. So we have another function from here to here. But you can also compose these things, because we start off with this person. I go from here to here, then down to there, and there to there, down to there. So if I can compose these 2 functions, I get a third function straight from here to here. Now, if you haven't seen this song before, you may think, you have to think, okay, it's obvious, but why do you make some dance about this? But it's a very fundamental idea. Now, believe it or not, ordinary mathematics is based entirely on just these ideas. You have these things called sets, and functions between sets. That's all there is to it. All there is to it. It's not true, but that's basically where you start anyway. So the composition of functions is the key property. So set theory is the foundation of all standard mathematics. Everything the physicists in the audience have done, I absolutely guarantee, unless they're very unusual, indeed, the place they work at, would have been done using mathematics based on set theory. And it is the foundation for classical physics. Now, if that was all there was, then I'd have nothing to say. I mean, quantum theory would just be peculiar and that's it. And critical realism would just be a bit hopeful and that's it. But in fact, there is a subject which I'm one of my things I'm really fond of. It's called topos theory. Topos is Greek. Now, how this works is it looks the same. What you try to do is you try to emulate the idea of things and functions between things. But the thing is no longer a collection of something. It's simply a thing. It's a letter. Call it what you like. Now, but you could do this at all was quite mysterious. In fact, one of the things that first attracted me to theoretical physics was when I was quite young, well, about 16 or so. I saw in a book the Schrödinger equations. Now, I never come across the Greek language at all, but I was supposed to be an engineer, see, so, and I saw this string of letters in Greek, which makes it look more mysterious. I thought, well, how can this be? How can it describe the world using strings of letters? Now, that sort of numinosity of strings of letters, in fact, it invades everything we do. Now, you may think, but hang on, then you're doing set theory, you haven't got strings of letters, you've got a collection of things. Actually, that's not true. If you look at the mathematical foundations of of set theory, what it actually really is, lo and behold, it's strings and strings of letters. If you actually look for a definition of these things, you'll find they something like will take millions, but vast numbers of pages to write down. There's lots and lots of Greek letters, one after the other. That's what a set actually is. It's one of these strings of letters. And all that happens in ordinary mathematics is you presuppose all this, or actually you don't. If you're a physicist, you don't even know it's there, but it is there. You manipulate these vast strings of letters. But rather than the vast string of letters for a number, you call it R or something, you see. So R stands for this vast strings of letters. So actually, all the time, what we're doing as scientists is manipulating vast strings of letters. Again, I find this absolutely extraordinary that you can do this. I mean, why it is the physical world can be described in vast strings of Greek letters, I've absolutely no idea, but it still seems to be true. So, rather extraordinarily, you can develop what's called a category, which looks the same as set theory, in the sense you've got things like this and what we call arrows between them, but they're not necessarily functions. And what is good, they can be combined. It's all you require. If you've got an arrow from there to there, another one from there to there, you can combine them together to get from one to there to there. Now you might think, well, that sounds really, really abstract, but actually it's not really, really abstract. As I've said, it's not really, really abstract at all. Now you might ask, well, all right, but does that basically were to work one of these things rather than sets and so on? Would you get anything like a logic? I mean, remember I said in classical physics you represent, or indeed ordinary classical thinking about anything actually, not just physics, you represent propositions about the system of certain subsets of sets. And that's what gives you the logic, a priori, in the Kant sense. The same thing applies here, because you do have things called sub-objects, these are things called objects. And the answer is no, in general. It's not the case that lots of these abstract things satisfy the axioms for this stuff. But they don't have logic. But there's something very, very special which was discovered in about 3 or 4 different ways. One of these extraordinary things that happens in mathematics sometimes. You have people working totally disparate branches of mathematics come across the same thing at about the same time, what you can call synchronicity, with no apparent link between them, but from quite different points of view. It's one of the things that always excites mathematics. When you see that happen, you think it's something really deep, actually. If the same thing's discovered by 4 people, totally different branches of maths, you think this is interesting. That's what happened with topos theory. Because it so turns out there's a thing called a topos, which is a special one of these collections of strings of English letters and symbols and so on, which in fact does have a logic, just like classical physics does. And what's more, the logic is distributive automatically. So your eggs and sausage and bacon, you don't get confused if you're ordering breakfast. It looks like classical physics. So you might think, well, if it looks like classical physics, what's the point? Well, the answer is it's subtly different. It's made up of a very slight difference. It makes a huge impact on the way you can use this. The only difference is this, it's almost Boolean. In ordinary Boolean logic, if you have a proposition P, it's identical to not P. So if I say it's not the case that my name is not Chris, that means my name is Chris. Now, in this type of logic, that fails. It only goes one way. So, if my name is Chris, it certainly implies it's not the case that my name is not Chris. But somewhat bizarrely, it's not the case that my name is not Chris. It does not imply my name is Chris. Now, you might think that sounds just as bad as the eggs and sausage and bacon, but it turns out that it's not. You can get used to that thing very, very easily. Once you've got used to thinking that way, it's actually very, very simple. Now, what is striking about this, and even if you haven't followed this so far, you can just sort of pick up this one point, is that one of these strange collections of letters and things and so on, any one of those is actually a possible foundation for mathematics itself. Now, to be clear about this, I don't mean a different branch of math, I mean an actual foundation for mathematics. This is really, really important. It's the actual foundations of maths. When I first discovered this, I was absolutely shocked, because I'm a through-going Platonist, and I sort of thought the foundations of maths are somewhere out there in the starry heavens or beyond the Neotic realm, which John mentioned this morning. Now, it's not having one of them out there. If you find there's billions and billions and billions of them, it gets a little bit, well, I found it uneasy, but it's true. I mean, one of the big debates anyway in the foundations of maths for many, long time, to whether maths is something we discover or invent. Is maths the creation of the human mind, or something we discover? Now, any mathematician you talk to who uses maths a lot, somebody like me, you always feel you're discovering it. Or if you're not, somebody else has. You feel it's out there, and you simply encounter it. It's just as real as the things are you do if you're an experimental atomic physicist or something. On the other hand, when I saw the fact this was true, I was a bit shocked. I wondered, well, maybe actually after all, mathematics is a creation of the human mind. It's not something up there. I really don't know. In any event, you have these things called topoi, or topos, and the sets is a special case. So mathematics we've used all these hundreds of years is just a very special case. Now, the question then immediately arises, why don't we use the other one, topoi? What's special about sets? And the answer is actually there's nothing special about the sets. And in fact, the following interesting historical fact is true. There's a great debate between Newton and Leibniz, remember that differential calculus. And broadly speaking, Newton was trying to use what we now regard as differential calculus in the way it's defined, what differentiation means. And what Leibniz was trying to use was infinitesimals. So he wanted to say, when you write dx by dt, but an infinitesimal dx divided by infinitesimal dt. Now, the first thing anyone learns when they do calculus at school or college is that you can't do that. There's no such thing as dx, at least not in that sense. You certainly can't divide dx by dt. Leibniz said there was. Now, it turns out it's quite easy to prove in ordinary mathematics that Leibniz was wrong. Is that the proof, you can easily prove it. However, it's just the way the proof works. It's what's called a proof by contradiction. In other words, you assume the theorem is false. When you prove that gives you a contradiction. And from that you deduce the theorem is true. But that's just what you can't do in these logics where only go one way. It's like, in fact, it's not the case my name is not Chris, doesn't mean it's Chris. So as a result of it, some curious factors, there are certainly foundations of maths where actually do have infinitesimals. So Leibniz was right. Now, if Leibniz had persevered and managed to persuade people this really was the way to do things, it seems to be highly likely, historically, we'd have been using these sorts of topoi, not sets. And some comments like this, someone would come along and say, wow, there's this thing called sets I've come across, which make everything look much simpler or something. So the question arises is this, and I'm going to ask this question in complete, genuine seriousness, is that maybe we're simply using the wrong foundations of mathematics when we do quantum mechanics. And maybe the same thing is true when you're doing philosophical discussion of critical realism. Now, if you think this is a bit far-fetched, let me tell you something bizarre that happened to me recently. I was invited to give a lecture. The LSE have sort of weekend gatherings for their students. Many universities do. They're new students. A lot of people go along and give them lectures. There's residential course, people drink a lot, sort of thing. You get to know each other. And I was asked to give a lecture on quantum theory, which I did. One of the other lecturers was talking about the problem of constructing a democratic voting system. Apparently, it's quite a deep issue. As he started to talk, I thought, my goodness, he's talking about a topos. We had a great discussion after this, absolutely true. The problems he was talking about could be circumvented by working with the different foundations of mathematics. It was the exact parallel of what we've been doing in quantum mechanics. So this is not just something, airy-fairy. There's a real possibility that this type of way of thinking about things can be useful all over the place. In fact, when I first started working with a philosopher, Jeremy Butterworth, he felt at the time that there had to be some application of what we do in the social sciences, because so many things we were talking about quite clearly with nothing to do with physics particularly. It does about logic in general, how you talk about the world. And I'm more and more convinced now that he said was true. However, you may say, well, okay, that's of course fascinating. Well, why is it anything to do with quantum physics? And the answer is this. In a topos, you find rather bizarrely, you can have propositions that are only partly true. Now, in ordinary maths, that's not the case. The proposition is either true or it's false. You see. I once, because of my interest in science fiction, I've met various entertaining characters over the years. One of them was the former Bishop of Birmingham, who was quite a forceful, Hugh Montefiore. You met him, he was quite a forceful character. And I was once taking part in some sort of public discussion with him, you see, and someone asked him, what do you think about life after death, you see? He said, if you're dead, you're dead, you see. So you're either dead or you're alive, you see. So are you alive? Well, obviously you're alive, because I think most of you are alive, obviously. But it's either true or false. But in a topos, the proposition could be only partly true. Now, if you're a quantum physicist, you immediately think of Schrodinger's infamous cat. In other words, the paradoxes of quantum mechanics look very, very different if you say that some propositions are partly true and partly false. And of course, in a way that you can control. And another thing, something may only partly exist. Actually, this is what finally turned me on to this particular branch of maths when I read this, because I am, let's say, keen on Heidegger and so on. I was actually quite familiar with Heidegger's profound reflections on the beingness, the beingness. And I thought, my goodness, what would Heidegger have said of this? If they can only partially exist. I mean, that's something that we just... If you read the whole history of philosophy, and I expect, well, I've read the whole history of philosophy, but at least I've read some, I suspect the whole history of theology. Nowhere will you come across the idea that a thing might only partly exist. I mean, everything is assumed to either exist or not exist, and certainly all standard philosophy is based on this premise. But that's just a coincidence, a happenstance of history. If Leibniz had won over Newton, we'd be used to the idea, I think by now, that things only partly exist. So yeah, this often fascinates me. I mean, I've spent all my life doing theoretical physics, so I kind of got used to it. But we take so much for granted. I mean, all the time we take so many things for granted. I mean, students do. We teach this is true, they believe you, and they become lecturers, they teach the next generation it's true. We keep repeating these things. Of course, to some extent they are true, but you know, how careful can we be? How sure can we be when we say something is true in science? It really is the case at some deep level. So, if history had been different, maths would be different. Now, how much time have I got left? Because it started a bit late, but I haven't overrun 10 minutes. Okay. Let me try to explain in 10 minutes how something can be partly true. Because this, I think, is, if there's any interest in this type of exist, how can something partly exist? And can you handle this? And you can, and all it requires is two pictures and some symbols. But, as I say, okay. Now let me go back to sets and the ordinary true-false thing. The thing we use for ordinary logic, ordinary daily talk, ordinary philosophy, ordinary theology, bog standard Boolean logic. Let me draw the picture I had before in a slightly more abstract way. Let me again consider the space of states, make it sound a bit more physical. And suppose K is some subset of states corresponding to some proposition, whatever. See? And let's look at the proposition that the element, the state S, belongs to K. Now, that's a mathematical proposition, not a physical proposition, of course, although it could have a physical sort of interpretation. But it's either true or it's false, because it's almost trivial. The proposition is true if S does in fact belong to K, and it's false if it does not. It's interesting about mathematics is unlike philosophy, there really is a truth about the matter. In mathematics, I mean, it's the one thing you can prove. I mean, you really do prove terms in mathematics, right? There's no question about that. You know what you're doing. And in mathematics, a proposition really is, this is what maths really is either true or false. So either this belongs to that, or it doesn't, you see. Now, that's of course obviously true. You can represent it in a rather sort of slightly more abstract way. I can say, right, well, let me associate to each state either the word true or the word false, which relates to K. So either it belongs to K or it doesn't. Now, obviously I can do that for any point in the space. It's either belongs to K or it doesn't. So either the proposition is true or false. So what I get is the function in this space into that space, to space of true or false, which, if you want, I could just write as 0 and 1. So it's just a slightly more abstract way. Now here comes the key point, which is remarkably powerful when you've got the hang of it, but it's rather abstract. When I've talked about elements in the set, you think, well, what I mean, collections of 5 numbers or so, it's obviously what I mean, but it's a little bit more subtle than that. But here's a rather fancy way of talking about elements. You see, what I said is this generalized type of mathematics, all it uses is diagrams and letters. You don't have actual collections of things. You just have letters like sigma. It's like purely relational. All the maths is about is how these arrows relate to each other. I mean, it's extraordinary you can do this, but you can. So let's try and write things in terms of nothing but arrows. See? And if we do, maybe we can take that across to these general things. It works, believe me. Here's the way you do it. Let's take once and for all the special set that contains just one point. Could be anything, could be me if you like, or John Pokemon. Yeah, so the set contains John Pokemon. Okay. Now, what does the function look like from here to here? Well, the function is something associated with each element here and element of there. But there's only one element there. There's only one point in there, just a point. So any function from here to here specifies a point. And conversely, any point, you can obviously construct a function from there to there. So, almost tautologically trivial, the elements are the same things as functions from this to that. Now, you may think, well, that's obviously true. Well, you may not think it's obviously true, but it is obviously true. But what is extraordinary is you can generalize this immediately to the following thing. Now you see, the truth value of the proposition is just this combination of arrows. The proposition that S belongs to K is now this function. So you take this point, star, it goes to S, and it goes to K. So into here, into that bit. It's just a composition of the two things, which is written like that. Okay, now I understand if you don't really mathematics, it may seem a bit abstract, but actually if you look at this picture, I think if anybody looks at this picture, but caught them out by themselves, not just high speed I speak at and so on, but you will see what I'm talking about. It's not complicated. What is extraordinary is how you can generalize this, and this is just how things can partly exist. Now, okay, let me emphasize again, this mathematics of partial existence is every bit as rigorous as the ordinary mathematics. There's nothing wrong with it whatsoever. It's just as good a foundation for maths, but you do have partial existence. And here's how it arises. What happens is, everything has discussed now in terms of arrows. So what we've got are these arrows, you see. So now we have the same diagram as before. I put the underline just to represent objects in this bizarre thing. Now, what is an element in this case? Now, I said we don't talk about sets, that's true. But you still have some analogue of elements because you have a universal thing called 1. Now, 1 is a very special object, and every topos has one. That's part of the definition, so you've got that. And then an element is now defined to be an arrow from there to there. So it's just, in other words, an element now is just literally that line on the... This takes some getting used to. You can talk with mathematics just in strings of symbols. You might think it's trivial, but it's not. So that's what an element is. And the analogue of the true-false thing is you have this thing over here, which again always exists on the top. It's called the truth object. And again, you can ask, well, does this element belong to this object? And the truth value for that is just going from here to here. But the thing about this is this object has more than just 2 truth values. Now what you find in a typical one of these topoi is that you have truth values other than true and false. You have like a nested thing, a truth at the top, that's like heaven, you see, and false down the bottom, that's hell. And then everything's spread out in between. So automatically, if you use this type of mathematics, a priori, you find propositions can be, of course, true, false, but also partly true. And that partial truth is controlled by the mathematics. It's not an ad hoc thing. You know, it's not just, oh, well, something's partly true. This is tightly and precisely controlled. And although it seems highly abstract, the fact is that you can actually use this sort of thing in practice, and you can find that propositions are, in fact, partly true. Of course, partly false. Now, what one can show, and I won't go into any of the details of this at all, is that you can rewrite quantum theory in this way, so that quantum theory looks like classical physics, but written just with different foundations. It looks exactly the same, actually. And this is quite bizarre when you see it, but it's true. Now, if this is true for quantum physics, I mean, just think what it does for other paradoxical situations, shall we say. If any point of ordinary discussion you come across something you want to talk about, but you find it somehow doesn't make sense, like quantum theory doesn't, and indeed arguably some things in theology do, the possibility arises if you shifted to a different one of these sort of perspectives, it would make sense. At least it would be controllable. Now, of course, as I say, this sounds speculative, but the mathematics is not speculative. I didn't invent the maths. I'm not claiming any originality for that. But the fact is you can do this. You really can do it. Now, whether it's useful or not, I don't know, for discussions, really, genuinely for discussions about science and religion. But I don't see why not, actually. Why should you suppose, I'll ask the theologians this in the audience, actually. Why should you suppose you can talk about God using just ordinary logic? I mean, why? If it's true historically that came about simply because Leibniz in the end gave up arguing with Newton, isn't it? I mean, speak of what John was saying about God interfering in the world. I mean, did God arrange things so that Newton won the debate, so that we invented set things, so that theologians could use ordinary logic? Or was it just, arbitrary? Could it have been different? Now, historically, it could have been clearly different. It had to be. You would think like this, I think. And I find that rather, striking myself. You can do this. So that's what I wanted to say. I say it's nothing to do with physics particularly, except it's motivated by physics. But I do think anyone who wants to use any type of logical argument about a domain of reality that's difficult, should we say, should take note of the fact that there are other types of logic you can use which are equally well founded. They're just as easy to use in a way once you've got the hang of them. But they may not have the paradoxes in that you're used to. And I think this is something that's worth knowing. So I started with this. I'm sorry if the talk's been a bit abstract. I took a bit of a risk with it, but I felt it was, different from my usual talks anyway. So, thank you.
Thank you, Chris, very much indeed. Well, we've got plenty of time now for questions and discussions. So, who wants to kick off? Yes.
I've got a few sort of comments, questions. First is, this reminds me a little bit of Bayesian probability theory, is that right? The second is, I suppose there are many different paths between 0 and 1 if you really wanted to do that, so you could make it quite complicated. But the most important question is, can you provide a really concrete example of where this is useful?
Well, the answer to the first question has nothing to do with Bayesian probability theory, not with signing appearance. The second one is that of course, there are different ways of getting from 0 to 1. That's not really what's important. What is important in any given situation? You may assign a truth value which lies in between 0 and 1. So, for example, if you're looking at Schrodinger's miserable cat, so you ask, is the cat dead? You may now find you have an actual answer to it. This is why it's to do with realism. You see, maybe this point hasn't come across. You see, the whole point about realism is you can give answers to questions, is this the case? Right. Propositions about the system, Heidegger's thing. But in ordinary mathematics, you have to give the true-false thing. That's what breaks down in quantum mechanics. But that's what breaks down other sorts of discourse too, like voting systems, for example. In this way of doing things, you still give answers to those questions now. It's something, but it's not just true or false, it's stacked in between. So it's a quite different way of thinking about what look like paradoxical situations. So if it's useful, well, I get gainful employment from doing it, it's what you mean.
Yeah, to clarify, if you've got sort of 0 meaning false and 1 equals true, you could say I'm going to assign a truth value which is somewhere along the real line between 0 and 1.
Well, it's not the real line, but anyway, yeah.
Well, but you could be really complicated and say there are innumerable dimensions which start at 0 and end at 1. Is that it done?
No, it doesn't work out like that.
It's just one dimension.
No,
between
no,
0 and
no,
1.
What's the set of this?
Let me be clear. Okay. As far as quantum theory is concerned, each physical system has a unique structure of this type associated with it. And it's not a continuous range of things between 0 and 1, but they're not strung out in a straight line either. They go out like that. They're partially ordered, they have width to them.
So there is more than one way of getting from 0 to 1.
Oh, yes,
more
but
than
that's...
one halfway parameter.
Yes, but that's not relevant because you don't use it like that. I mean, the thing, once you use it, this replaces probability in quantum mechanics. You don't need probability anymore. What happens is rather than having, this is the whole point really, rather than having the statement of probability of something as a third, say, instead you get these generalized truth values of what the value actually is. And you can show you can get back the probabilities from that. So this is why I call it a realist view, because it's giving you answers to say, is the spin up, is the spin down? No, is the cat alive, is the cat dead? It gives you an answer to that question always. So if you take the spin along different directions, which you know normally don't commute, say sigma x and sigma y, it will give you an answer to the question, what is this spin and what is that spin at the same time, which you normally couldn't with the uncertainty principle, but you can do this now because the extra logic gives you room for it. So it replaces the probabilities. And in that sense, it's a realist theory, but it's not a realist theory using sets.
Chris, I think where some of us may have blinked is your penultimate slide. You showed
Yes.
a slide where things were either true or false. And then you said, I'm going to show you one where they can be something
I said the
else.
orders were simply away from me, so I thought I'd do it very quickly. So
You succeeded in doing it quickly.
Are you especially interested for me to repeat this transparency? Because this is the key
There's
transparency.
a concept which isn't sufficiently clear in my mind.
Okay, let me take 5 minutes to explain this. If you look at what this looks like in sets theory, you have what's called a truth object, which is typically 2 elements, true and false. You call them 0 to 1 if you like. Each one of these topos is something called the truth object, which is just one of these things in this collection of letters and so on. But each topos has a unique one, and you know what it is. And that's called omega. Then you have things called objects. Now I've represented here this sigma as an object, you see, it looks a bit like the space of states. And you have things called sub-objects. So just like you have subsets, you have sub-objects. They're not really called subsets, but they have the same sort of relation. And you have this notion of a generalized element. But an element is simply defined by this arrow from here to here. Like I said, in ordinary set theory, you can do this. You can define an element by a function from a single point, which does seem bizarre when you first see it, but the point is you can generalize it in this case. Now again, in ordinary set theory, there's a unique thing called a set for the single point, which is a set for the single point. So here, each topos has a unique one of these. So you have a unique one of these and a unique one of those. That's given by mathematics. As a result, if you look at the proposition, this element S belongs to K, if you look at what it actually means, you'll find it's mathematics. It's just the same as it was in classical physics. You simply go from there to there, from there to there. You compose these 2 arrows together. And you end up with an element of omega because you've got something which is taking this point into there. So omega does have some points in it, but they're not just true and false.
Is there some simple example where we can actually see what this omega is? I mean, I have a hard time.
Well, there are, but not perhaps suitable for your general audience. I mean, yeah, there are some simple examples. In mathematical sense, some very simple examples, but not perhaps for audience like this. But
is it some high-dimensional space?
No. It's just it's a set of things. I mean, it's
a finite set, or
no? Another complication is like Bohr was very wise, really. Bohr said you have to look about the world using classical language, right? This is part of the great debate about Copenhagen interpretation. In a sense, he was right. I mean, it is true in a sense. If you talk about measurements, you do use classical language. Now here, you use set theory as a meta language. So you talk about this sort of mathematics using the language of sets, which sounds mysterious at first, and a bit of a fiddle, but it's not. So the answer to your question, Don, is that using the meta language of set, you can construct things like this quite easily. And you can construct examples quite easily which have more than just 2 truth values. And in particular, that's true of every quantum system, manifestly. So every quantum system has each one has one of these attached to it. This is peculiar because each quantum system comes with one of its own topos, but each topos is the foundation for mathematics. So each quantum system comes with its own foundation for mathematics. I mean, that sounds strange. But again, that's not a sort of conjectural statement. It's simply a true fact. Now, it may be useless, but it is true. Each quantum object comes with its own foundations from mathematics. It's quantum mathematics with a vengeance. So that's what the picture means. But of course, it doesn't mean you have to see it working right before you really get the hang of it. But it does. And well, quantum theory, I didn't go into that. What they look like in quantum theory. But yeah, sorry.
As you vary h bar, you vary your quantum system. Do you continuously vary your topos that you're using to that extent?
All theoretical physicists with h bar equal to 1, so the question never arises. H bar has to do with the fine details of a quantum mechanics type of system. That's interesting. H bar has dimensions, and dimensions are due with space and time. To talk about things with dimensions, you inevitably introduce spatio-temporal concepts. So you need to build up to these things slowly. I mean, you have to be very, very careful. If you really are doing taking sort of thing seriously, you have to be extremely careful what you do step by step, so as not to do something daft. So in order to do this H bar, you need to introduce space and time as well. We haven't done that yet, but you could do it. So this is a research program, it's not finished, but I thought that basic idea is sufficiently interesting to be worth talking about to a general audience.
But maybe just to get an example, suppose the quantum set were a two-state system, like a spin that could be up or down. Is that what?
Well, then these are finite sets.
So
these things. So in the meta language, they're finite sets, yes.
Is it, and is the set just determined how big? I mean, does the set just determined by the Hilbert space of this thing?
Yes.
Or also
Yes, you need
how big is it?
Give you an example of what I mean by this, and this is a good example of John's mentioned. Take a very simple example of a single electron, which everyone loves to play around, which talks about the meaning of quantum theory, or a pair of electrons, even better. You can then construct these things explicitly. Now, if you do that, then you find this thing, I call sigma, can be easily described in terms of sets. It's not actually a discrete thing, but it's easy to describe. There's lots and lots of points in it. However, if you shift out from the meta language into the actual language of the topos, you find there's no points at all, in fact. So what we're talking about is there's a subject called pointless topology, some genius of a mathematician, but in fact quantum mechanics itself works with what looks like a state space with no points whatsoever. And that's equivalent to the Cochran-Specker theorem, actually. Okay. So this is
Omega
Omega does have internal points as well as external points.
And how many? I'm confused.
Well,
how many points does Omega have if you just have a two-state system?
It's lots, but not lots in a particularly non-trivial way. I mean, it's just because you can. And you mentioned you have a continuous range of possible directions. It has to accommodate all of that, but it's just basically it's a small number. I mean, it's essentially small.
But I mean, is it a continuum or a finite discrete integer?
It would have the card. I think it would have this case. We haven't actually worked this case out. I think it would have the cardinality of the continuum.
Okay.
We thought about doing it. We haven't done it yet. Yes.
Yeah. Suppose that omega has 3 possible values. Would I be able to label them 0, 1, and 2?
If you want to label how you like.
Yeah, but it would also imply that if you say that so omega has 3 values, and the one I call true, the other one I call false, the third one I call partly true, then would I interpret that partly true is mutually exclusive from true and false?
The principle of non-contradiction applies in this sort of maths. It must always. As I say, you can never assert the proposition and its negation at the same time. It can never be true. What can be true in these things is that you don't have excluded middle. When I said you have that P implies not P the other way around, another way of saying that is that the same thing is ordinary logic. You have P or not P is equal to 1. That's the so-called excluded middle. Now that's not satisfied here. P or not P is generally speaking, smaller than 1, if you like. That's the only caveat. Apart from that, you can manipulate these things as you would ordinary logic. I mean, the point is this, you see, the mathematics of this is fixed. All these so-called intermediate truth values, the maths of them is absolutely fixed by the theory you're looking at. It's not arbitrary. It's specifically specified. How you label them is up to you, but there wouldn't be it would be a bit disingenuous to call them 0, 1 and 2, because they wouldn't behave like the numbers 0, 1 and 2. You have to call them A, B and C, actually. Or 0, 1 and C or something. Safer.
Yes.
I don't understand maths, but I just wanted to understand the implication. It almost sounded as if you were saying, instead of saying we don't know if it's this or this, which is kind of probability, we could definitely say it's probable. Do you know what I mean? I'm not quite sure. Is it just a rewording of the same problem, or does it actually have? Does it make a difference how the world works?
You have to be careful what the "it" means in this. I mean, The answer is yes in a sense, but you really do. I mean, one has to be careful how you say this. But that's the broad idea: is you're replacing probability, which is usually interpreted instrumentally, with true-false values, which can be interpreted realistically in realist terms. That's the whole point of the whole thing. Is you don't have to. You can keep. In a sense, don't have to be an instrumentalist. You see, the way quantum mechanics is normally presented, either you're an instrumentalist or you're lost in many worlds or all sorts of whatever. See? And what was to say is actually it's not true if you change the foundations of maths itself. But clearly it's not just true about quantum theory. Like I've said, I mean, voting, democratic voting systems, who'd have thought? They work better with different foundations of maths, but they do. So the potential implications of social sciences are fascinating, actually. Maybe that's where it has its greater use, for all I know. I mean, I might say, our reason for doing all this is not in fact to get another interpretation of quantum theory. It's to find theories that go beyond quantum theory. As I said, I belong to the school of thought that thinks you must change quantum theory, talk about quantum cosmology. And the question is how you do that. And the idea of all this was to find a way of changing ordinary quantum theory, actually.
I wondered in a sort of a macroscopic sense, you know how people say, there could be multi-universes, and there are lots of other sort of things that people spin out of quantum theory. Does this change some of the...
Well, in a sense, it can
things change.
In fact, I didn't go into the details of this, but you could argue, I would argue, actually, that this, in fact, when you do this in quantum theory, what you actually get is a mathematical representation of what we might call multi-universe theory. But see, most people, when they talk about multi-universes, they just use strings of words. They draw pictures of things. They don't actually... It's not a complete mathematical model, or very rarely. This kind of is a complete mathematical model. And it is, I haven't given the details, but if you want, you can interpret it in something like the multi-universe language. But, like I said, this is not speculative. I mean, what's there is what's there. You know, if you take a particular example, you say you want to look at free spin half particles, okay, we can work it out, because that's it. That's what it looks like. Better or for worse, that's what it is. And you will see, I mean, what I didn't say in quantum theory, the truth, it's not just multi-value, it's contextual. This is the subtlety. Is that in quantum theory, the truth of a proposition depends on the context in which you assert it. Now, this is a very deep result, actually. It's a bit like, there's these two great schools of, two great ways of interpreting truth. There's the correspondence theory of truth, which most scientists take utterly for granted. Is something is true if it corresponds to what is actually the case. Then there's the coherence theory of truths, which say, well, you shouldn't talk about the truth of a single proposition. You have to look at the whole body of things. It's how they cohere together that works. And in a way, this works more like coherence theories of truth and correspondence theories. But it does work.
Good. Any other questions? Yes.
I guess I'm still wondering why I should be happier about the statement Schrodinger's cat is half dead than the probability of Schrodinger's cat being dead is a half.
Well, it depends what you want to do with it, see. If you want to do quantum cosmology, you see, if you're actually, Schrodinger's cat, you can say, well, cat's a cat, But if you want to do quantum cosmology, you can't. In quantum cosmology, you cannot accept, in a useful way, a statement of probability of a third. If you look in the box, you find the cat dead. So you have to find some sort of realist interpretation. But ordinary quantum mechanics does not have an ordinary realist interpretation. What this is saying is that you can do it, but you end up with, in ordinary language, contextual truth. So like I say, the truth of the proposition depends on the context in which it's asserted, and also the truth is multi-valued. But once you've got that, you could manipulate it as if it was ordinary realism. This is the whole point, really, that in other words, when you argue using this sort of mathematics, the way you argue, because the exercise in Bacon's works, you use the same sort of logic almost you do in ordinary daily discourse, and like quantum logic, it's much, much easier to use. That's why you can base mathematics on it. So if you really are interested in the foundations of quantum mechanics in that sense, this is a certainly interesting way of thinking about things. But for quantum cosmology, you get driven towards how to think about these things anyway. Like I said, I didn't really want to talk to you about this because it's the way of doing quantum theory. I'm just struck by the fact this is a different way of talking about the world using logic, which is not wild. It may sound strange, but that's not the same thing. All math looks strange the first time you see it. I mean, that's true of anyone who studies math too, of course it does. When you've got used to it, it's not strange at all. It's just as easy as said theory, actually. It's just different.
Yeah, a kind of logic I came across some years ago was fuzzy logic, which has...
that's a special case of this.
Oh, right, okay. Well, that's helpful, yeah, because that had partial truth.
Yes, that's right. That's a special case.
Yes.
I have a question maybe of understanding. I think I heard you say that when P is true, that implies that not P is false, but not vice versa.
Strictly speaking, it implies not P. You have to state things very carefully. P implies not P, but not P does not imply P necessarily.
Does that mean that not P is not, if P is a proposition, not P is not a proposition?
It's not that. It's where the question about existence comes in. You see, this is also a proof by contradiction. See, proof by contradiction works exactly this way. You assume that it's not the case. You assume that P is not true, you see. But you prove that's false, so it's not the case that not P. And from that you deduce P. This is the standard technique in mathematics for proving things. Now you can't do that in this sort of maths. But many mathematicians anyway have said this, quite independent of this sort of thing. They've said that proofs like that are dubious. You know, to prove that something is true, you don't really want to prove that the contradiction is not true. You like to actually show directly that it's true. I mean, it's a whole, for hundreds of years, but at least for almost 100 years, schools of mathematicians want to do this anyway. In fact, that's one of the origins of this sort of stuff, is people working so-called constructive mathematics.
Maybe some further question here. I think the suggestion of your talk was also that this structure that may apply to the logic of quantum theory could, that there's also a link with theological statements.
Absolutely. I mean this perfectly seriously. I'm usually very, very careful about talking about my own research in general talks. I think it's usually a bit pretentious and also usually incomprehensible. But on this particular case, because I really do believe it is a way of talking about other things, I thought it was worth doing.
Do you mean that a statement in theology, for instance, God exists, that is a statement for which you do not have to say that it's true or false?
Yeah.
Something in between.
But the point is you can manipulate the statement just as well. I mean, see, one gets so used to things being true or false that you think, if it's not true or false, there's somewhere fuzzed in between. What can you do with it? But the answer is that you can do a lot with it, actually. Yes, that's right. Yeah.
I think you ought to try to compose a didactic example whereby you invent some topos with some new properties. It doesn't matter what they are so long as they're simple, and then develop these into a world in which this applies and just demonstrate the consequences of all of this. And then I think you'd sell your ideas more easily because people would understand the consequences more easily.
Of course, I completely agree with you. I'm well aware of the sociology for spreading ideas. I mean, that is why I was struck by the thing about voting systems. In fact, the guy who gave the lecture, who was an economist from LSE, I'd never met before. We actually said, we should write a paper on this together. Well, but of course, you know what happens, you get back and you have emails and things, nothing ever came to it. So I agree with you. But this math is very difficult to do properly. My collaborators, we had to prove some very difficult theorems. And we only published this stuff like 2 months ago in its final form. So we're working on examples, but this just takes time. I know very well, as a scientist, extremely well, to sell something like this, which the maths is very difficult for theoretical physicists to read, you've got to have a killer example. I know that very, very well. And that's what we would like to do, because we would try to do. See, what this is the toolkit, right? It's not a theory of anything. All this is the toolkit. What it's saying is you can use in your toolkit types of logic which are different from what you thought, which are just as good for founding rigorous discussion on. That's really what I'm trying to say. It's a toolkit, but of course, to show a toolkit is useful, you need to show that the tools are useful. Couldn't agree with you more.
Yes, and then
if I understand this correctly, I must say it's not so strange, really, to say that if you have three objects, to say that if you prove one is true, that's the normal approach. But if you prove that not two is true, then you haven't proved that one is true. It can be three or whatever. Is that?
It's a bit subtle than that, I think. But,
is it?
Yeah.
Or is it?
Yeah. I mean, it's equivalent to excluded middle. Yeah. So you have to think about what it would be like if P or not P is not automatically true. It's not false. It's not automatically true. And that's you see in a sense where the generalized truth values come in, because if P or not P does not automatically true, because you sense the idea things will be partly true.
I think it works with raining. I've been trying to find an example.
Raining?
Because if you say, is it raining? You can say, it's raining. And then you can say, definitely, that's right. It's not raining. Okay. But if you say, is it raining? And you say, it's not raining, then it could be it's somewhere in between raining and not raining.
Anyway, well, that's true, but more precise actually is where is it raining? And philosophers often discuss this. The phrase "it is raining" or "is it raining?" it can't be answered without the context of where you mean. Like I said, this stuff most naturally fits in with contextual logic. So the question "is it raining?" has no answer. Is it raining outside or there, outside? And if you think about it like that, then it does become a bit clearer actually. That, Andrew.
Chris, I wanted to ask whether, in terms of the theological cash value of these ideas, you're saying this may provide a mathematical paradigm shift which may in due course affect the way we think theologically, or are you saying you already have mapped it onto some theological... Sorry, just to finish my question. That you already have mapped it onto some theological concepts, in which case can you give us an example?
No, it's not that. I mean, I've over the years been involved in many science revision things, and I stopped doing them after a while, sort of about 10 years ago, because I felt we kept repeating the same thing over and over again, and I got a bit fed up talking about the heart of all the universe and so on. It didn't seem to go anywhere. But I did learn a lot, because I got to know many theologians. I did talk to some of them in great detail, particularly process philosophers, actually, interested in Whitehead. And if you read Whitehead, which I did try to read seriously, you begin to realise that Whitehead's mode of thinking is not normal classical thinking. He's trying to use concepts in quite an original way. And at one stage, actually, a chap called David Paley, you may know him, who's a professor of process philosophy in Manchester, he and I were going to write a book together, actually, about the quantum version of Whitehead. That was the idea. I mean, it was sort of been Whitehead up to date. I mean, we started doing it, but we couldn't for various psychological reasons, basically because he was Aristotelian and I'm a Platonist. It didn't work. But I realised, listening to people talking seriously about theology, and sort of Bob Russell's like, these meetings we go to, that actually, if you really think about it seriously, I'm not a theologian, of course, right, so I can't contribute to theology, but listening to the way people argue, you really realise that actually they do assume an awful lot about logic, which may not be a priori true. I mean, it is a priori true with the way they argue about things. I mean, for example, you will hear theologians using proofs by contradiction, see, things like that. Now, maybe that's not legitimate. I doubt whether theologians would think about that. Maybe they would. I don't know. Maybe I'm wrong. It's unlikely. So, of course, I haven't applied it to theology. I'm not a theologian. I wouldn't know quite where to start. But when I was talking to David Paley, we did have some idea there of doing something really genuine. But very, very difficult, of course. I never underestimate the difficulty of theology. I mean, anybody can be a theologian, actually. Actually stand up and talk about God always seems to be quite amazing. I can do that.
Yes.
I just wanted to ask, you mentioned you published something just recently. Could you give us a reference?
Well, after all on the web, of course. I mean, when I wrote the first time, was this philosopher in Germany. That was about 8 years ago. We got stopped at a certain point. And it's actually essentially we didn't quite understand what we were doing, to be honest. Didn't quite say that in the papers, but I knew it was true. Then about 18 months ago, I started working with this Austrian, a German guy, Andreas Doring. Suddenly the block was swept away and went up like a rocket. So it's all on the internet, as the answer. If you just type Isham Topos, you'll get all the hits you want, more probably than you want.
Well, on the subject of publication, you alluded to a New Scientist article that thinking about the popular understanding of science. Could you just tell us a little about that then?
Yeah, I mean, I know someone vaguely who's a journalist on New Scientist. He wanted to write an article about me, so he did, and it appeared on New Scientist. And the front page, it was the front page story about a month ago. It was had a big blackboard of eggs and sausage and bacon on it, but they got it wrong. And I kept trying to tell them it's this. The desk editors, these blasted desk editors, they always think they're better than the author. Not that I wrote the paper myself, I didn't. But I could see what I got sent a draft, and I objected to all sorts of things, including some things said about me. But anyway, they left those in. But they also left in the mistakes. And it's hopeless to these people. You can't do it. They actually think they know better than you do. So that's the only. What is missing at the moment is any sort of remotely popular discussion of this. I mean, if I have time this summer, I want to write something which is accessible to people and not pure mathematicians. I mean, my own colleagues don't understand what I'm doing at the moment. My fellow physicists don't understand the maths. And they won't bother to understand it either unless they can see it's worth their while, which means when they get promoted with the Nobel Prize. So that's right, that's what you're saying. So you have to really convince them. But to do that, it often pays to write a very simple thing. We just pull out the critical points, free of all the actual formulas. But of course, to do it honestly, you must prove all the theorems first. You see, I hate use the word bullshit in such a gust. I hate doing that. I always, when I lecture, I always try to tell the truth, or else I don't know. So I'm very, very careful never to talk about something unless I actually know it's true. So there's a lot of hard work gone behind all this. I mean, I've never worked so hard anything in my life, actually, for the last 18 months. I've been absolutely flat out. Really hard work. But now it's done. Now we can ourselves step back and think maybe we could write sort of a much more general thing, really accessible to anybody, actually, that was interested in use of logic, talk about the world. So I hope we can do that. But it's not done at the moment, so I'm afraid the only articles are highly technical. Well, you have some words at the beginning, too, a quote from Heidegger.
So are you not recommending to read the New Scientist article as a popular, accessible insight into this?
Well,
I mean, is that...
if you want to read what a wonderful person I am, you can read it.
Oh, right, okay. Let's talk about that. Okay.
But apart from that,
It's
I wouldn't personally recommend it. But it's interesting. It's caused a lot of interest on these discussion groups on the internet, because these days, you see, it's not just what your colleagues think. You know, it's what the world thinks outside. It's amazing how many more hits you get now to Isham and Topos, because I check from time to time, because of that article. And if you read some of these, you know, some of the people say, oh, this is fantastic. Others say, this is pretentious rubbish, you know. They don't know me, of course, personally, anything, you see, but some say it's wonderful, some say they do, you see. People talk about it, it's not scientists. So in that sense, it creates a lot of interest. So the internet, in a way, is a place to check these days. The internet's a fantastic tool. Absolutely fantastic.
Anyone? Yes, John. Just
I guess maybe. Oh, I must admit, I'm one of those that hasn't yet studied this to look into it. But maybe to get to both, I'm a little curious because I would have thought that you could do quantum mechanics with ordinary logic. It's just that the propositions are not the same. So in other words, if I had a two-state system and then classically I might say, well, the spin could be up or down, but then quantum mechanically I won't say those are properties. So then I could just say the property is, if I consider this thing by itself, I could say that the property is that it has a density matrix. And so, you know, it is true the density matrix is such and such, or it is false that the density matrix is such.
You could say that for individual propositions. I mean, there never was any problem in quantum mechanics talking about individual things. I mean, individual propositions, I mean. It's collections of them which don't commute as a problem. I mean, David.
Right, but I mean, suppose I just say that this two-state system, if I consider it with self, not. I mean, of course, it's tricky because it can be entangled with something else, and then of course you have to consider the bigger system. So whatever your biggest system is that you include, I mean, maybe it has to be the universe. Whatever this biggest system, what if I just say, okay, it's completely described by its quantum state, and its quantum state is described by giving the expectation values of all operators. Of course, maybe for the whole thing I need to know the operators in their algebra. But I mean, suppose I know the operators in their algebra and the expectation value in the state. I mean, suppose I said that's a complete set of properties, so the whole state fits Heidegger's definition of a thing.
They're not the properties, they're the properties of the results of measurement. It's something quite different. The expectation value...
No, but what if you just interpret it as properties of the system? I mean, instead of...
Well, it's not what people mean by it. I mean, people don't, by the properties of the system, people don't normally mean the expectation value. Apart from anything else, that depends on the state. The property is a state-independent concept. Right? In classical physics, for example, the notion of state doesn't depend on what you actually... physical quantity you're talking about.
Right, but I mean, if it... Well, for example, in this two-state system, in the classical thing, it could be either spin up or spin down. But so I suppose quantum thing, I agree, it does not have the same properties. But suppose I say that this thing, it does have a density matrix, so I can just regard it as, you know, some vector with a length not greater than 1, the polarization vector. And suppose I just assert that's a complete description of this of the
You can do that, but
the
that's what
system.
people are concerned with. I mean, they want to talk about the spin in this direction and the spin in that direction. The sort of things that quantum theory says you can't talk about.
Right. So I guess for that I would say, well, that's not a property of this system. Of course, if I couple it to something else, I can make a measurement and correlate it with one memory unit, and then maybe I could take another measurement and correlate with another memory unit. So then, of course, I'd have to include that whole system.
When you do that, you're just bringing in the instrumentalist interpretation. I mean, in effect, what you're saying is you can use ordinary classical logic to talk about the results of measurement, which of course is absolutely true.
Well, but I wanted to regard that as a fundamental property of the system, and I don't have to think. I mean, in other words, if I imagine doing it for the whole universe, of course we don't know, but I mean, let's suppose the whole universe can be described by some set of, well, there's some set of operators. I mean, and then a state would just be given by a C-star algebra. So it just gives you expectation values of all these operators. So I mean, I guess what I would think is that could. Why can't I regard that as a complete description of the universe?
Why should you? Why would you? I mean, one thing you say depends on the state. Of course, if you believe it's
well, of course, but the state's part. I mean, the state is the thing that gives.
Well, in the end, as you know very well, I mean, we invent these things as theoretical physicists. We can invent what we like.
Right.
But what I'm saying is, if you want to use logic in even remotely analogous to the way it's used in any other field of study, then you do encounter these problems of quantum logic, and then you do have to decide what to do. I mean, if you want to say that you only can talk about the results of measurements, if that's what you're going to do from the very beginning, or expectation values, then of course you can do that, but then you're in a different game from what I'm talking about.
Yeah. So maybe it's a different. I mean, admittedly, I suppose in the back of my mind, I would think that this, you know, the operators and the expectation values.
And that's mathematics, all right. The question is how you interpret the maths. We have operators too.
Right. Well, I suppose for that I would go into my well, what I either call sensible quantum mechanics or mindless sensationalism. And as to just say,
I won't ask you which of the two categories you put my talk into.
No. That's two different names. Two different names for my crazy theory. So, or my crazy framework.
Well, you see, I take these questions highly seriously. I want a non-crazy answer. I've been trying to find something which you can say which is unequivocally true about. Now, it may not be useful, but it certainly is true. I really do think we have to be awfully careful when we talk about foundations of quantum theory, not to get too caught up in science fiction. I mean, the problem with science fiction is it sounds very good, particularly for the general audience. It's terribly tempting. I mean, I've heard some appalling talks. Sometimes some of these, the Vatican organised these, as most of you know, these series of meetings, and I went to several of them. And I've heard some diabolical talks from some of my colleagues, where really they've just taken the latest bit of speculation from the latest version of physics, whether about wormholes and other. They spend the whole talk talking about this thing, which is totally speculative. I mean, even the physicists say complete speculation. It seems to me that's theologically absolutely useless.
Well, I guess we don't know what's the fundamental. I mean, okay. I mean,
no, you don't know, Don, but you know quite well people just read these theories every day. They come and they go. I mean, it seems to me, well, I think anyway, if you want to take these sort of things seriously, it's no good to us as physicists, I mean, keep throwing at the theologians and everybody else, the general audiences, just our latest random, crazy theories. You want to say something, if you can, that's might even be true.
All right, okay, well, I said in sort of a self-deprecating way. I mean, I suppose I seriously do think that this is the right way to interpret quantum theory. Not, it's one proposal. I mean, maybe it's so. I think in yours, as I would understand it, the topos would be, and then certainly.
Well, as I said, our purpose is not actually to get a new way of interpreting quantum theory. It's get a way that gets way beyond standard quantum theory. See, we'll think about this. Let me just say a final word about this. Right. If you take this form, don't ask me to start. If you take ordinary quantum mechanical field of spaces, right, you say, how can we generalise this and get away from it? It's actually very difficult.
Right.
It's very obvious statements like you use quaternions or something, but broadly speaking, you're stuck with the same thing.
Right.
And that's been a big problem for a long time. So you have classical physics here, you have quantum physics, they're totally different. Oof, what do you do?
Right.
But this sort of formalism, you see that classical physics and quantum physics are both special cases of a general thing. That's the whole point, really. You see, is that one is the top of the set, and there's another top. But apart from that, they're the same thing. You see, there's a lot more to what I've said. For example, we have an almost proved conjecture, so let me say it's only a conjecture, but it's almost certainly true, is that classical integration theory in the topos is the same thing as quantum expectation values viewed normally. And also, I think it's almost probably true that if you do classical computation theory in one of these toposes, you'll get quantum computation theory as normally perceived. So, in other words, you maintain, as it were, the really interesting aspects of quantum theory, but you're no longer tied to Hilbert spaces at all. And you can see, therefore, really ways of getting away from quantum mechanics.
Yeah. Well, that's a really exciting thing. If you have a different way of formulating it, that allows you to do a generalization.
That's my real personal motivation.
Yeah. Okay. Well, that I guess what you just said now excites me. I think maybe the other part I didn't quite.
Yeah. No, I think very motivation.
I think probably it is tea time, and I know we've had quite a long session now. It would be a great discussion to carry on, and I think there will be more time for discussion and indeed over tea. But I think probably some people here would like a cup of tea.
Me particularly.
I'm sure you do. I mean, you're very hard, Chris, and it's really stretched our neurons. And it's been a fantastic talk, especially for biologists as well. So thank you very much.